Okay, so in the previous video, I showed you the simulated results, how the graph changes when the scale of experiment increases. When the sample size you observe in one experiment increases, then there are three patterns we find from different uh, shapes of dice. First, the mean looks like the same. Pattern 2, the variability decreases. Pattern 3, normal distribution. So the first one can be formulated in this way, which is pretty simple. Simply speaking, the expectation of the average equals the expectation of the single variable. So no matter you throw like 100 dice or one dice at a time, their average, the expectation don't change. Expectation is expectation. See, you may prove it like in a simple two dice case, because we know that by the identical distribution assumption, the first dice and the second dice must be the same dice, right? And then their average can be written in this way. And then by the linearity of the expectation, you can rewrite, and the 1 over 2 can move out of the expectation, and the expectation applies to each of the variables. Then you will get, in the end, they are the same thing added and then divided. So just only one remains. And property number 2, the variability decreases the shape of the graph. Shape of the graph is more like a concentrated around the mean. And then it can be formulated in this way. The variance, the variability of the sampling distribution is inversely proportional to the scale of the experiment, right? So the numerator is the original variance. Original variance when you throw one dice. This is the case when you observe only a single outcome, one dice, and then if you throw two dice, then the variance will become 1 over 2. And if you throw 100 dice, for example, then the average's variance equals the original variance divided by 100. So as you increase the scale of the dice, then the variability will decrease as the variance decreases. Of course, standard deviation follows if you take square root. So the denominator becomes square root of n. So square root of n, square root is applied when you change variance into standard deviation. And you may do the same thing. So remember, when you multiply something inside variance, it becomes squared when you move it out of the variance. That's the key part here. So actually you are multiplying 1 over 2 here. So the dividing by 2 is multiplication of 2, like 1 over 2. And then when it comes out of the variance, it becomes 1 over 2 squared. So like there are two 1 over 2s. One of them is cancelled because same variance is added. Still there is one remain. So as a result, denominator still has 1 over n. So 1 over n is still multiplied. Okay? And finally, pattern 3. The distribution of x bar converges to a normal distribution as the sample size increases. As the scale of a single experiment increases, the sampling distribution of the average converges to a normal distribution, which was clear from the graph. So again, what's amazing about this pattern, particularly property 3, is that the original shape can be anything. can be anything. Like as I showed you, fair dice, unfair dice, like unfair in whatever way, will anyhow in the end will become normal as you increase the number of dice you throw at a time. In other words, so then you see how powerful this is. You don't need to know what is the underlying distribution. I don't know what is the how the dice looks like. What I only need is the parameters, the mean and the variance, which is easy to calculate. So if you can calculate the mean and the variance, then automatically you can apply them to the normal distribution. So like no matter what variable you have, you know everything. As long as you calculate, you already know, and also you already know the variance and the mean. Mean and variance are known, and as a result, with this property, you know everything. This is this is the most powerful result in modern statistics. So maybe you may have heard about this theorem before, the law of large numbers. There are two fundamental theorems in statistics. One is this, and the other is coming in the next page. So one is the first fundamental theorem in statistics is the law of large numbers, which means the mean is the same, but the variance decreases, and in the limit as n goes to infinity, the variance goes to 0. So when variance goes to 0, that means it becomes a constant. X bar becomes a constant. The variance of the average goes to 0 means the average becomes a constant. So you can say this. As the sample size increases to the infinity, the randomness in the average disappears, and the average converges to the true population mean of a single variable mean, right? That is that's the law of large numbers. The sample mean converges to the population mean. That's the meaning. Okay? And central limit theorem. This is the second fundamental theorem of statistics. Central limit theorem uses normal distribution. So, like when n is large enough, the average is approximately normal distribution with mean. By the way, remember it's not x bar. This is the mean of the underlying distribution. And in the numerator, like here in the variance, this is also the variance of a single observation. So if you have a single observation variance, then you know the sampling distribution, right? So let's put it this way. So remember, single observation is just one person's income, and X bar is the average of 1,000 people or a research center's report of the average income, right? So they are different. You have to think them differently. They are using different experiments. So this expectation and this variance are coming from the single observation experiment, but this X bar is coming from a large scale experiment. So it's very confusing, but if like you have to imagine what we are talking about and what I'm using here. So then the question is, like when I just said sufficiently large, how large is sufficiently large? There is no scientific way to say one is like this is large but this is small. It's just like simply speaking, the larger the better, the more the better. But in many textbooks, the threshold is usually set as 30 or 35. but as I said, 35 is still very small. So, and particularly in economics, we have the sample size usually at least several hundred. Or these days, like think about the annual income data. I don't know how many. So in my course example, there were like several thousand observations. So in serious research, like it could be like million, right? So then usually this is not a big problem. Of course, still the more the better. The larger the sample size is, the normal distribution approximation is the more accurate. So the distribution becomes closer to normal distribution. So then let's go back to the original example of income survey. So first, we will start from the single original experiment of X. X is the annual income of one person. So X is just for one person, and I assume that the parameters are like this. The mean of so if you randomly choose a person, then on average, the income will be 50,000. And standard deviation will be 10,000. Just suppose you know the true parameters. However, you know the mean and the variance, but the distribution of X is not normal. Usually the income distribution is skewed to the right, because there are super riches like Elon Musk is like Elon Musk, Bill Gates, Jeff Bezos. They make a thick tail usually in income distribution. So the distribution is not normal distribution, but we don't need to know what it is, as I said. And now for numerical example, now I'm going to reduce the sample size to 100. The survey samples only 100 people and calculate their sample average of 100 people's income. Now what we can do here is, so suppose that like I gave you the true values, true mean and the true standard deviation, but suppose that the research center or the economist does not know these true parameters. So that's why he or she is doing the survey. Now what we can do here is we can calculate the probability that this economist's average is underestimating the true average by more than $3,000. Right? Let's see what we do. So what we are going to do here is we would like to calculate this probability. We are looking for the probability that the economist is underestimating more than $3,000. That means the sample average the economist calculates X bar, and it should be smaller than $47,000 because we know the true mean is 50,000. So then if it's smaller than 47,000, that's exactly what we want to calculate. And in this case, X bar is a random variable. It depends on who are included in the survey, right? That is random. If you choose different people, then the calculation result would be different. If you happen to have Elon Musk in your sample, then you are screwed. You are going to overestimate the mean a lot. So anyhow, it is random. So we can think about this probability. It is random, so there is probability. And also we can think about its mean and its standard deviation because X bar is random, right? But we may use the earlier results, the results that I showed you this video. The mean of the sample average is the true average. the true mean of a single person. So 50,000. So remember, this expectation is for the calculated average by the economist. But this expectation is the true expectation when you choose one person, not 100. If you choose one person at random, you are going to get 50,000. But if you choose 100 people, also the average is 50,000. But the standard deviations are different. Standard deviation of the estimation results by the economist is this one. And this is the standard deviation of the income when you choose a random person. When you choose one random person, this will be standard deviation, and we know that is 10,000. But the economist will have a smaller standard deviation because she chooses 100 people at a time. So the denominator, the standard deviation, is divided by square root of 100. Of course, you know square root of 100 is 10. So as a result, the standard deviation of the economist estimation result is 1000. That means, like, remember, we wanted to study the distribution of x bar. And we know now we just calculated x bar's expectation and standard deviation. That means, because we know x bar follows a normal distribution approximately, these two can serve as their parameters. These two, we just learned the parameters for the normal distribution. This variable is approximating, right? This variable is approximately a normal distribution with these parameters. So by the central limit theorem, which means it is approximately normal, then you know how to use this. We learned how to calculate probability for non-standard normal distribution. Here we are. So first, you standardize. Smaller than 47,000 will be standardized by x bar minus its expectation and divided by its standard deviation. These are the parameters necessary to standardize. And remember, the other side of the inequality must be standardized in the same way, like this. And we know the values. Here, standard deviation of x bar is 1000. Remember, you have to divide it by square root of n, right? What I gave you here is for a single person, not for a survey of 100. So to convert the standard deviation, you have to divide it by square root of n. And then after the standardization, you have z, standard normal distribution z, smaller than -3. Then you use Excel calculator, normal distribution calculator, standard normal distribution calculator tells you it is 0.135%. That is the economist has a very small probability of underestimating by more than $3,000. So if you go, this is exactly going from the parameter to the data. So we are going the other way. So now I gave you the true values of the mean and the variance, and then we consider how this economist estimates the mean, and then we calculated the error probability. But what we do in practice is exactly the other way. We are this economist. We should be this economist, and we have to learn how much error my estimator can have. So that is what statistics does, the ultimate goal of statistics. And remember, this is the basic law of large numbers. and central limit theorem are the basic fundamental theorems to do that. So I hope this example serves as a good example to show you why we are doing this chapter, why we are learning sampling distribution. So from this, we can calculate the error probability of an estimation. So we are going to utilize that in the next chapter. By the way, okay. So in the next video, that's what I said here. In the next video, I will start another example of insurance. This is not about estimation, but it's a very interesting example. And maybe you may have, some of you may have learned like microeconomics about microeconomics of like economics of uncertainty. How insurance, what is insurance economically in theory? So we will analyze how insurance works in the next video. See you later.